Hi, my name is Mark Wilde, and I'm going to give a talk about my work with David Ding, Sumit Khatri, Yihui Quek, Peter Shore, and Wang. This is an extended talk for the Beyond IID conference. Yihui will be giving a lightning talk during the live event. So yes, this is work that we did probably over the span of 2 years roughly. And our original goal was to bound the classical capacity of a quantum channel assisted by classical feedback. But in the process of doing this project, we found other things of interest. And so and that's related to bipartite channels. And so I'm going to tell you about that also. Okay, so what is the motivation? As I said, we're interested in the classical capacity of a point-to-point quantum channel. What I mean by that is there's a sender and there's a receiver, and those are the only participants involved. And this classical capacity is a fundamental measure of the ability of the channel to send classical information. This problem has been studied for a long time. This is probably one of the earliest problems considered in quantum information theory. One of the fundamental results is due to Alexander Halevo in 1973, the Halevo bound. And, there were some other results that came along from the 70s to the 90s, but then the subject really took off again in the 90s with the advent of quantum computing. And now it's really gotten studied a lot. We know a lot of things now. So why is it interesting? It's interesting because the theory predicts that in principle, there can be significant gains in communication rates if we have access to quantum strategies for this basic task. So that's the main reason. Today, in this talk, I'm going to focus on two variations of this problem. I mentioned it at the beginning. One is the forward classical capacity of a bipartite channel. I'll discuss later what a bipartite channel is. And then we'll also talk about the classical capacity supplemented by a classical feedback channel. And this problem of assistance by a feedback channel, this was studied for the fully classical case by Shannon in 1956. It's a famous result in information theory that this feedback channel does not increase the capacity of a classical channel. But in quantum information, we have access to the resource of entanglement, and so this changes the picture quite a bit. And it's known, a result due to Graham Smith and John Smolin, that in fact, for some channels, there can be tremendous gains from a classical feedback channel for the classical capacity. And that's due to entanglement. So what we're trying to do here is to understand this a bit better and place upper bounds on the feedback assisted capacity. So let's do a bit of review. What is a classical communication scheme? Let's suppose that Alice and Bob are connected by a quantum channel. Mathematically, this is a completely positive trace preserving map acting on the space of density operators. In a classical code, we'll talk about a one-shot code, and we'll parameterize it by two numbers, m, the number of messages, and epsilon, the error. Okay, so a code consists of, it's parameterized by those two numbers, and it consists of an encoding channel and a decoding measurement channel such that this error condition is satisfied. Okay, so this is one way to describe the error. This is an average error probability constraint. So over here on the left, we have the ideal state that we'd like to generate at the end of the process, which is a maximally classically correlated state. And then this is the actual state generated by the physical process of encoding, sending through the channel, and then decoding. And we want this error to be less than epsilon. M is the number of messages. It's the dimension of this Hilbert space, the message Hilbert space. Okay, and the goal of the scheme, as indicated, is to preserve classical correlations. Okay, and if you want a picture, I'll show you the picture now. I previously described a one-shot code. This is an nshot code where you're using the channel big N, little n times. And so you send the message through the encoder, through the channels, through the decoder, and you try to decode. And Alice and Bob are physically separated. An example of a channel would be a free space communication channel, say like Earth to satellite. This gets studied a lot for quantum key distribution purposes. Okay, so this is a code. How do we define capacity? Let's start by defining the one-shot classical capacity. And this is simply the largest number of bits that you could send using any possible encoding scheme such that there exists an epsilon code. The one-shot classical capacity is a function of two things. We fix the channel, we fix the error, and then we try to maximize the number of bits that we can send, which is log base 2 of the number of messages. The classical capacity is this asymptotic quantity. Okay, so we allow many uses of the channel. So we plug in a tensor power channel. We normalize by the number of channel uses. We take a limit for technical reasons. It's the limit inferior. And then we minimize over all the errors from 0 to 1. And that is one way to define classical capacity in a very compact way. Intuitively, you can think of this as the maximum rate at which you can send classical information such that the error tends to 0 in the limit of many channel uses. That's how you can think of it intuitively. And so the classical capacity is an asymptotic concept. There's another related concept of interest. It's called the strong converse. You simply flip the infs to sups, and then you get this strong converse classical capacity. Okay, and this has been an important concept in both classical and quantum information theory. This is possibly the most compact way to define it. Another way to think about it is that if your rate exceeds the strong, if your communication rate of your sequence of communication schemes exceeds the strong converse classical capacity, then necessarily the error probability will tend to 1. And something that you look for channels is whether you have a match between the classical capacity and the strong converse classical capacity, because it significantly enhances our understanding of capacity if that property holds. Okay. One thing you can see from the definitions is that the classical capacity is always less than the strong converse classical capacity. That's the picture I showed before for n-channel uses. So what's known about this problem? A lower bound is known. I don't know if I gave a reference here. It looks like it did not. It's due to Halevo, Schumacher, and Westmoreland. Halevo had a paper in 1996, and Schumacher and Westmoreland did also. So this is a lower bound on the classical capacity. This is called Halevo information or chi information. And it's a formula that looks like Shannon's formula from the classical regime, but the quantized version of it. So you maximize this Halevo information over all possible input ensembles. So I didn't define the mutual information, but it's the entropy of B plus the entropy of X minus the joint entropy of X and B. And that's with respect to this classical quantum state. And so you can see that this is a measure of classical correlations that can be generated using the channel. So that's a known result. It's a lower bound, and it's an important result. It's a quantum result because to achieve this lower bound on the capacity in general, you have to allow for a collective measurement at the output. A collective measurement can be implemented by doing some joint unitary on all the outputs and then product measurements. And so to do that, in general, you would need a quantum computer. Okay, for certain channels, we know that the Halevo information is equal to the classical capacity. So that's a nice result. There's a collection of these channels. A famous example is entanglement breaking channels. Peter Shor showed that. Okay, but a breakthrough result, it's now over a decade old, but it was a breakthrough at the time, is that in principle, there exists a channel for which there's a strict separation between the Halevo information and the classical capacity. So that tells you that in general, this Halevo information is not equal to the classical capacity. One thing you can do, I didn't show it here, is you can regularize the Halevo information. You can plug in a tensor power version of the channel and normalize by the number of copies and take a limit. That's called the regularized Halevo information. That is known to be equal to the classical capacity, but it's really just a formal mathematical expression for the classical capacity, because that's going to be hard to calculate, if not impossible to calculate in general. Okay, let's talk about bipartite channels. So this is a different channel model. In the quantum regime, one of the first appearances where this channel was made was in a paper of Bennett, Harrow, Leung, and Smolin about capacities of bipartite Hamiltonians. So here we're allowing for more than just unitary evolution, but we're allowing for channels. So the model is that Alice has access to this input and this output port of the channel, and Bob has access to this input and this output port of the channel. And so the channel has a richer structure. It generalizes point-to-point channels. And because the parties involved have access to both the input and the output of the channel, if you want to be general, this allows for richer encoding schemes that incorporate adaptive operations between every channel use. So that's what we're going to consider here. Okay. And that's exactly this kind of scheme. So this is exactly the kind of picture we're going to consider. This is a scheme for forward classical communication of this classical register from Alice, from her laboratory, to Bob's laboratory, by making use of the channel and by making use of adaptive local operations between every channel use. So this is a depiction of a scheme for forward classical communication that uses the channel 4 times. And of course, this can be generalized to little n uses of the bipartite channel, big N. So what is a code? Here, we really only, we have to consider nshot codes where we use the channel n times to really have a sense of what's going on, because you can have these adaptive operations. That was not the case for the unassisted classical capacity of a point-to-point channel that we considered before. We were not considering those adaptive operations. So now we have 3 numbers that parameterize a code. It's the number of channel uses, the number of messages that you're trying to send, and the error probability with which you can send the messages. Okay, so we're going to define a classical communication code like this. Here's the picture of the scheme. You can describe it mathematically. That's something we did in our paper that's posted to the archive. I won't do it here. You have the picture and so you can see it. But really the error criterion is that the final state, we'll call it this omega state between the reference and b hat, that should be epsilon close in normalized trace distance to the maximally classically correlated state. So that's the criterion we'll adopt. There are other different criterions you can adopt. And again, this is an average error criterion. Okay, so that's the definition of a code. And then we can define the capacities in a similar way as we did for the unassisted capacity. So first we have the nshot forward classical capacity of the bipartite channel. And that is the maximum number. So it's a function of the number of channel uses, the error probability epsilon, and the channel itself. So subject to those constraints, you simply try to maximize the number of bits you can send through the channel in the forward way, such that there exists an NM epsilon protocol of the form we talked about on the previous slide. So that's the nshot capacity. And then the forward classical capacity, we define it in the same compact way by taking limits. So, and again, this is intuitively the maximum rate at which you can send classical information in the forward direction from Alice to Bob by making use of the bipartite channel many times, such that the error probability tends to zero as the number of channel uses becomes large, okay? That's the intuitive description. This is the compact math. Again, we have a strong converse. We flip the imps to sups, and then this property holds, directly from the definitions that the capacity is less than the strong converse capacity. Okay, so the capacity is a hard quantity to calculate. People have tried for years to calculate these things, and it's difficult. So what we do is we give ourselves a little slack. Maybe we give up a little bit on getting it exactly, and we instead try to bound the capacity, and we try to come up with clever ideas for bounding it. It would be nice if the bound is efficiently computable. Okay, so that's what's going on with this STP, semi-definite programming. What we're going to be showing is a semi-definite programming bound for upper bound for the classical capacity. That means that this bound will be efficiently computable. Okay, so how can we do that? We're going to come up with a quantity that's equal to 0 for a bipartite channel that's non-signaling from Alice to Bob. Okay, so if the channel has no ability to send any information at all from Alice to Bob, it's non-signaling, and we want the quantity to be equal to 0 for such a channel. And then furthermore, we want it to be equal to 0 for a channel that has no ability to generate what I call useful entanglement between Alice and Bob. So those are the two conceptual ideas, and those translate into precise things mathematically. Non-signaling has a precise description mathematically, and I'm not going to give that here in so much detail. For that, you can look in the paper. We have a paragraph that talks about that. And then this no ability to generate useful entanglement, that means something precisely mathematically. That's PPT preserving channels. And for further details of that, you can look in our paper. PPT is positive partial transpose. So those are the two things we're looking for in a measure. We want the measure to be equal to 0 for such channels. And so that will translate into getting a bound on the classical capacity assisted by these local operations. And furthermore, the classical capacity of a point-to-point channel assisted by classical feedback from Bob to Alice. And then, local channels will satisfy these two criteria. So in the figure that we showed previously, these are local channels. We want the measure to be equal to 0 for local channels for all of these. And the basic idea is going to be to evaluate the measure on the whole scheme, relate it to the parameters of the code, and then it'll obey what's called a subadditivity property. So the measure evaluated on the whole protocol will be less than or equal to the measure evaluated on the sum of each individual step. And then if the measure is equal to 0 for the local channels, then we'll get all that will be left is the measure evaluated on the individual channels. That's going to be the main conceptual idea. There's a lot of math involved in showing that. But that's the basic idea. Okay, and this idea was inspired by earlier work of my co-author, Wang, where he was using these concepts to get STP bounds for the unassisted classical capacity. I don't know if I said it, but these two constraints, non-signaling and PPT, are semi-definite constraints. And so that's the very nice thing that allows us to get efficiently computable bounds. Okay, boom. Now here you have it. This is the quantity. It looks very complicated. And it took a lot of time to come up with this, to get the proper thing. So we're going to define this measure with respect to a completely positive bipartite map. That generalizes mathematically a bipartite channel to include maps that are not necessarily trace preserving. So we're going to define this C beta quantity. It's a generalization of a quantity from Shin's work. That's something that we'll see later. And it's defined in terms of this beta quantity, which is this optimization. And so, we can try to explain this as best as we can, and there's only so much intuition, but you have this objective function, and this is measuring, in some sense, we're exploiting an isomorphism between channels and operators, and that's what's going on here. So given the bipartite map, there's something called the Choi operator. This appears a lot in quantum information. And so S is kind of, there's a map from the S operator to a bipartite map corresponding to S. And this objective function is measuring how close this S operator is to being trace preserving. How close is it to being a channel? So that's some intuition behind it, okay? And this other constraint is related to the PPT constraint that I talked about before. We want the measure to be 0 for a bipartite channel that has no ability to generate useful entanglement. So that's related to what's going on here. And then this constraint here is related to the no signaling constraint. So if you've studied the mathematics of no signaling constraints, this kind of thing will look familiar. So this is a semi-definite constraint. This is a semi-definite constraint. And then we have this other constraint relating S to V. Okay, that's in a nutshell. And then we have computer programs available with the archive posting of the paper. So if you're curious to play around with this quantity, you can download those programs and evaluate this measure for bipartite channels of interest to get a sense of it. What are the properties of C beta? C beta is this log of beta that we defined here. I'm just going to list them. I'm not going to go through the proofs, because for that it's long proofs that are available in the paper. First off, it's non-negative. That's the kind of thing you would expect for a correlation measure, or a measure of classical correlations that can be generated by a channel. Another thing is that it's stable under tensoring with identity channels. So if you tensor with identity channels, those will be local channels. You can say this identity channel belongs to Alice, this identity channel belongs to Bob. And that's important. If you go back to the scheme for communication over here, you see that this bipartite channel in this step is being tensored with a local identity channel here and a local identity channel here. And so the stability says that the measure evaluated on the whole thing will be equal to the measure evaluated just here on the actual channel. So that's important for the proof. Another property is that it's equal to 0 for a classical feedback channel from Bob to Alice. That will be essential for the application to bounding feedback assisted capacity of a point-to-point channel. Another thing that we already said is that it takes a 0 value for a tensor product of local channels. We also said it should be subadditive under serial composition of bipartite channels. So if we have a bipartite channel M1, and then we compose that with M2, the measure evaluated on the composition should be less than or equal to the sum of the measure evaluated on the individual bipartite channels M1 and M2. So that property holds. That kind of thing is essential for bounding feedback assisted capacity. In all the proofs I'm aware of for bounding feedback assisted capacity, you need this kind of property. And then this is a consequence of some of these properties, but the measure it does not increase under pre and post processing of a bipartite channel by local channels. I believe that's a direct consequence of properties 4 and 5. It's also invariant under local unitary channels. So if you apply local unitary channels before and after the use of the bipartite channel, then the measure doesn't change. That kind of thing is expected for correlation measures as well. And also it's convex. So if we have a convex combination of bipartite channels M1 and M2, the measure evaluated on the mixture is less than or equal to the mixture of the measures on the individual channels. Okay, so those are the basic properties of the measure. But as it turns out, we can follow something that Eric Rains did in like 1998, 2000, 2001, somewhere around that time frame, where you start with this basic measure, and then you can do something to improve it further. And so that's what we're going to follow here. So to do that, let's introduce what's called generalized divergence. And this will give us like a whole infinite number of measures, you know, that could be useful for a variety of things. So a generalized divergence is some mathematical function of a state and a state sigma and a positive semi-definite operator, such that this inequality holds. So the divergence between the state and the operator does not increase under the action of a channel. So this is called data processing, and it's a property obeyed by any measure of use and interest in quantum information. Okay, that includes relative entropy, trace distance, like a flipped fidelity, renu relative entropies, etc. We're going to make two minimal assumptions about a generalized divergence. You know, if it's a function of a state and an operator, an example of a trivial state is in fact the number one. That's kind of a funny thing if you've never thought about that before, but the number one is a quantum state. And so we make this requirement that if the second argument is less than or equal to one, then the measure is non-negative. That's obeyed by many divergences of interest. Another minimal assumption is that it's equal to zero if the first and second argument is the same. That's a very minimal assumption. Okay, then from the generalized divergence for states, we can define what's called generalized channel divergence. This is a concept that my co-authors and I introduced in this paper, but it's really a generalization of the well-known concept of diamond distance in quantum information. So we're just replacing the trace norm with the generalized divergence. And so the channel divergence is what you get just by taking the state divergence and optimizing overall states that can be input to the channels. And following the spirit of the previous slide, we allow for the first argument to be a channel, but the second to be a completely positive map. Okay, and then this is a key quantity of interest in this work. This generalizes a concept introduced by Xin Wang and Kun Fang in their papers. So this is called Upsilon information of a bipartite channel. And so what you do is you take your channel of interest and you compare it in generalized channel divergence to all completely positive bipartite maps such that the beta quantity is less than one, okay? And so this turns out to give tighter bounds and be a more useful measure than C beta itself. And one thing you can prove pretty easily is that C beta will, you know, be greater than or equal to this Upsilon information. So if you're trying to give the tightest upper bound, it makes sense simply to go to the Upsilon information. Okay, so this is what we're just saying. You know, it obeys many of the same properties, but it leads to a tighter bound in general. A key choice of interest is the geometric renu relative entropy. This is a concept introduced by Petz and Riskai and developed quite a bit further by Matsumoto and Vishal Kataria. And I, you know, did some more things with it in a very long paper, kind of established more of its properties in more detail and explored it further. So it's defined like this. So let's get to the point. What is one of the main results that we have? It's this statement here. We talked about nshot forward classical capacity of a bipartite channel. This is the kind of bound we can give. It's a finite length bound. It applies to finite n, finite epsilon. And so it should be useful for more practical applications, non-asymptotic quantum information. So we get the Upsilon information derived by setting the generalized divergence to be the geometric renu relative entropy. We get this bound plus a correction term related to finite size effects. So that's the kind of thing we get. And then by taking a limit as alpha goes to, by applying the definition of asymptotic capacity and strong converse asymptotic capacity, you take a limit as n goes to infinity, this thing goes away. You take a limit as epsilon goes to 1 for the strong converse, the epsilon's already gone, so all that's left is this geometric Upsilon information. The bound then holds for all alpha greater than 1 and less than 2, so you can take the limit as alpha goes to 1, and when you do that, you get something called Bilovkin-Stashevsky relative entropy. So this is one of our first major results, this bound on the strong converse classical capacity of a bipartite channel. So let's look at some examples. It's always nice to look at examples to understand the bounds and to see how good they are. So here's what is called a partial swap unitary. It's been considered in the literature. It's kind of like a finite dimensional analog of a beam splitter, where it's like, you know, a beam splitter, if it's fully transmissive, then it does a swap. If it's not transmissive, then it implements an identity channel. It implements local identity channels. So the partial swap is some kind of quantum superposition of those two possibilities, and that's why it's called partial swap. And P, this parameter P tells you like how close you are to doing a swap or how close you are to doing the identity. So this is the kind of bound we get. If P equals 0, then the channel is a product, it's an identity channel, which is a product of local channels. And a product of local channels has no forward classical capacity. So the bound evaluates to 0 for that case, and it's consistent with what we'd expect. In the case that P equals 1, the channel is a full swap, okay? And the bound is actually tight in that case also. Remember, this is an upper bound. It evaluates to 2. Why is it tight? There's a simple scheme for achieving the capacity of 2, and it uses superdense coding. So I'll just describe it in words. So on a first channel use, Alice cannot send, and this is the case of a perfect swap, okay? So on a first channel use, Alice cannot send more than 1 bit to Bob, okay? But what Bob can do in that first channel use, since they have a quantum swap, is he can send in 1 share of a Bell state to the swap. And then in the next round, Alice and Bob will share 1 E-bit of entanglement. So they can use that as a resource for superdense coding. So then Alice can do superdense coding on 2 bits and put that, a qubit, through the swap operator, through the swap channel. And at the same time, Bob can feed in another share of a Bell state. And then they can iterate this procedure, and in the large N limit, they achieve 2 bits per channel use. So it's a very quantum strategy they can make use of for forward classical communication. This thing is not possible, this kind of strategy is not possible classically, because you wouldn't be able to generate the entanglement between every channel use. They could just generate like random bits, and that would be no good for forward classical communication. One thing we did not do, and is the subject of investigation, is to determine how tight the bound is for all the values of P between 0 and 1. And to do that, we'd have to look at a strategy of Bennett, Harrow, Leung, and Smolin in their work. Another example of interest is a noisy cnot gate. So the cnot appears a lot in the context of quantum computation. This is a noisy version of it. It's saying that either you apply the cnot with some probability, or the qubits being input get destroyed with some probability. They get destroyed and replaced with the maximally mixed state. So that's a noisy cnot gate. And again, we can evaluate the bound for this channel. However, in this case, this channel has symmetries. It's what we call bicovariance. And for details of that, you can look in the paper. I'm not going to go into it more here, but there, instead of using the geometric renu relative entropy, let me go back a bit to talk about this. Instead of using the geometric renu relative entropy, you can use the quantum relative entropy. And so in general, you're going to get a tighter bound. And that's due to the symmetries of the channel. It's called bicovariance. So if you evaluate it, you get this bound. So when p equals 0, you're implementing the cnot, and then it's known that the forward capacity of the cnot gate is just 1 bit per channel use. And then when p goes to 1, it becomes the completely noisy channel, which has 0 capacity. And then this is an interpolation between those possibilities. And whether this is achievable, it's something that we did not do in our paper. And again, we can consider possible strategies for seeing how tight this bound is. Let's talk about the final application. So this is going to be the classical capacity assisted by classical feedback. So what I'm doing now is, this right here is a classical feedback channel from Bob to Alice. And this is a point-to-point channel from Alice to Bob. And so this is what a scheme looks like for classical communication over a point-to-point channel assisted by a feedback channel. And this is 2 uses of the forward channel and 2 uses of the feedback channel. And you might notice that all I did here, let me go back a bit. I have to go back a bit, sorry. All I did was I took this picture, I replaced every odd use of the bipartite channel with the feedback channel. That is a special case of a bipartite channel in which this system is trivial and this system is trivial. And the other thing that I did is I replaced every even use of the bipartite channel with a point-to-point channel, such that this system is trivial and this system is trivial. And then we get the picture shown over there. And that gives a general scheme for classical communication assisted by classical feedback. Okay. And then a code is defined very similarly to how we defined previously. An N-M epsilon code consists of little n uses of the channel big N, and it's such that the final state obeys this criterion, such that the classical correlations are preserved up to some epsilon error. Okay, so that's a classical communication code. The capacities are defined very similarly. You have an nshot capacity. It's a function of 3 things: the number of channel uses, the error epsilon, and the forward quantum channel, the point-to-point quantum channel. So it's the maximum number of bits that you can transmit, the maximum rate at which you can send classical information, it's the maximum rate, such that there exists a protocol of the form discussed in the previous slide. And again, we have the feedback-assisted classical capacity defined in the same compact way, the strong converse feedback-assisted capacity. And then again, a straightforward consequence of definitions is that the capacity is less than the strong converse capacity. Okay, so then what we can do here is we can take all of the measures defined previously for bipartite channels, and we can evaluate them for point-to-point channels. Why is that? A point-to-point channel is a special case of a bipartite channel in which Bob's input is trivial and Alice's output is trivial. Okay, and so the measure then reduces to this measure, which was found by Shin and colleagues and Runyao Duan and another co-author in their prior work. Okay, so it looks like this. This is a semi-definite program also. Okay, and then you can have this derived quantity for a point-to-point channel. This appeared in later work of Shin and Kun Fang. Okay, so the theorem that we have is very similar to the previous one. It's that the nshot feedback assisted capacity is bounded from above by the geometric Upsilon information plus a correction term related to the finite size parameters. Okay, and then it's the same reason as before to get the asymptotic bound, and this is a strong converse bound. So you just apply the definition that we wrote previously for strong converse. Here, you take the limit as n goes to infinity, take the limit as epsilon goes to 1. And as you take when you take the limit as n goes to infinity, this goes away. You're left with this. The bound holds for all alpha greater than 1 and less than 2. You take the limit as alpha goes to 1, you get this. And that's the upper bound. So it's a new strong converse upper bounds on the feedback assisted classical capacity. Prior to this, there was not a general strong converse upper bound on feedback assisted classical capacity. David Ding and I showed that the Halevo information is a strong converse upper bound for entanglement breaking channels, where we couldn't show it for other channels besides that. And so what this new result is the first general bound on feedback assisted classical capacity. And what it shows is that the quantity proposed in this prior work, its proper place is as an upper bound on the feedback assisted capacity. And so it leaves room that there could be a better upper bound on the unassisted capacity as an open question. So let's look at a final example. A very important channel commonly considered in quantum information is the depolarizing channel. And why is that? It's like a worst case scenario channel. It's just, and it's simple to describe in terms of a single parameter. Either the qubit goes through with probability 1 minus p, or it gets destroyed and replaced with a maximally mixed state. So it was established in a recent work of Kun Fang and Hamza Fawzi that this Upsilon information is an upper bound on the unassisted classical capacity of a depolarizing channel. But what we show is that, as I mentioned previously, this quantity is an upper bound on the feedback assisted capacity. And if you're paying attention really carefully, you notice I didn't put the hat. That's because the depolarizing channel has lots of symmetry. It's a covariant channel. And so you can get rid of the hat and use the relative entropy instead of the Bolovkin-Stashevsky relative entropy. Okay, so we have that upper bound. And then we know that the unassisted classical capacity is equal to the Halevo information. So there's nothing further to do for the unassisted classical capacity. And this is what we find. So this is the depolarizing channel. When p equals 0, it's a perfect qubit channel. When p equals 1, it's a totally useless channel. So you see those two extremes reflected here. For a perfect channel, the capacity is 1 bit per channel use. For a useless channel, it's 0 bits per channel use. And then this is the Halevo information lower bound. When p becomes 2/3 or greater, the channel becomes entanglement breaking. And so then we know that from my prior work with David and prior work of Gary Bowen, that the Halevo information is equal to the capacity assisted by feedback. But then at this line, this is now the best that we have. The Upsilon information is this upper bound. So you see, at least we have an upper bound better than like just 1 bit per channel use, which was actually not really known for a while. And we instead have this Upsilon information. So that's the latest result that we have. And you see that there's plenty of room for improvement. So there could be other ideas to improve this bound. So I'll stop there. What we did in this work is we established several measures of classical communication, and we proved that they find use as upper bounds on classical capacity, both of bipartite channels and point-to-point channels assisted by classical feedback. An obvious open question is whether the bounds that we gave can be improved. I showed this on the previous slide. There's tons of room for improvement. There was a recent paper by the Fawzi brothers, Hamza and Omar, about techniques for improving bounds based on geometric renu relative entropy. That will be presented at the Beyond IID, I believe, by Hamza Fawzi. And as a key example, I really wonder about the depolarizing channel, if classical feedback could actually improve its capacity. I have no idea about that, and it would be very interesting, in my opinion, to solve that question. And then another question is, does this new bound improve on a bound from prior work? So in a prior work of David, Yihui, Peter, and me, we showed that the maximum output entropy of a point-to-point channel is a weak converse upper bound on feedback assisted capacity. And one thing I wonder is how does this new bound relate to that? We didn't show anything in general. So that's an interesting question. Okay, let me talk about some of the references that I mentioned since they're here and since there's time available. This reference was for the partial swap channel. In this paper, they had other concerns, but the partial swap channel appeared here. Gary Bowen and his co-author worked on feedback assisted capacity of a quantum channel. This was one of the first works on this topic. This right here is the paper I mentioned with my co-authors about the maximum output entropy bound. This I mentioned briefly. This is a paper that David and I worked on around 2015. And we gave strong converse bounds for the feedback assisted classical capacity of entanglement breaking channels, kind of a particular topic, but we were just trying to make progress on feedback assisted capacity in that work. I mentioned about geometric renu relative entropy. This is a very impressive paper that used this. It was the first one, I think, to show how the geometric renu relative entropy is really useful in quantum information theory. That will be presented at Beyond IID. This is the new work of Hamza and Omar that will be presented at Beyond IID. This is a paper that I wrote with co-authors. We talked about the partial swap channel there as well. It was about a totally different topic though. It was about something called quantum interference channel. Hastings had the results about superadditivity of Halevo information. Chris King established the capacity of the depolarizing channel, the unassisted classical capacity. Vishal and I had a very lengthy paper that we wrote during the quarantine after it hit back in March. And we showed how geometric renu relative entropy is useful in other applications like channel estimation theory and discrimination theory. This is the paper I wrote with Felix and others about, and we had generalized channel divergence in there. Keiji Matsumoto wrote papers about geometric renu relative entropy also. Dennis Petz, about geometric renu relative entropy in his work. This was a paper about generalized divergence in the classical case. Shannon's famous paper about feedback assisted capacity. This was about generalized divergence for the quantum case. And these are some of Shin's papers about getting SDP bounds on unassisted classical capacity that inspired the present work. Thanks a lot for listening, and I'm looking forward to seeing everyone at Beyond IID.